Okay, so we already measured half a wavelength dipole antenna. So the current setup that you see is for the E-plane measurement of half a wavelength dipole antenna. Now I want to convert this half a wavelength dipole antenna to full wavelength dipole antenna. So 1 lambda dipole antenna. So to do that, I'm gonna remove the two arms of the dipole, and I'm gonna replace them by bigger arms. So this is the arm for the half a wavelength dipole. This is the arm for 1 wavelength dipole antenna. So I'm just gonna use these new arms. So now I have my full wavelength dipole antenna. And as you see, this is a still E-plane setup for E-plane measurement, and we're gonna go ahead and perform E-plane cut measurements for this dipole antenna. So similar to everything we had so far, I'm gonna turn on the RF power at 1 gigahertz, and I'm gonna start the acquisition on the system. Okay, now we're gonna start collecting the E-plane cut pattern of full wavelength dipole antenna. So we start the acquisition, and now it's plotting. And while it's plotting, you can also compare its relative pattern to the half a wavelength dipole antenna. So as you probably notice, it is more directive. So this new antenna, 1 lambda dipole antenna, is more directive, and but the received signal level is smaller compared to half a wavelength dipole antenna. Okay, now that we have finished this, we could, for example, save that as a new antenna in the E-plane. So one thing I want to just mention is that if you look at the half a wavelength dipole antenna, this is the half a wavelength dipole antenna, and this is 1 lambda dipole antenna. So as you expect, it's more directive. The length of the antenna is larger for 1 full wavelength dipole antenna. But on the other hand, the signal level is smaller than half a wavelength dipole antenna. So it's almost in the order of 5-6 dB smaller, and that's counterintuitive based on the fact that we know that the directivity of 1 lambda dipole antenna is larger than the directivity of half a wavelength dipole antenna. So the question is that why the signal received by 1 lambda dipole antenna is smaller as compared to half a wavelength dipole antenna. So if you want to understand this, you need to understand that herein we are not measuring the directivity of the antenna. We are measuring the received signal. So when we are doing that, the impedance mismatch at the port of the antenna also plays an important role. Now, if you remember from the class, 1 lambda dipole antenna has a very high impedance at the input port. So you're going to have some impedance mismatch, and because of that impedance mismatch as compared to half a wavelength dipole antenna, you get a smaller signal. So that this experiment demonstrates that 1 lambda dipole antenna is more directive. So you can easily see that it's more directive. And the estimated one that we have on here is 79.94 for half a wavelength dipole antenna and 57.63 half power beam widths for 1 lambda dipole antenna. So the one for half a wavelength dipole antenna is very accurate, but the one for 1 lambda dipole antenna can still be improved. That should be around 48 degrees theoretically, but it's 57 right now. Uh, so, but this essentially shows that it's more directive. But on the other hand, you know that it suffers from impedance mismatch. I'm talking about 1 lambda dipole antenna. Therefore, the level of the received signal will decrease. From the experiment, we just observed that the pattern of the half a wavelength dipole antenna was very similar to this black curve that I plotted here. And the pattern of 1 lambda dipole antenna, as we just measured, was very similar to the red curve. So from these two plots, you can immediately see that the red curve has a smaller half power beam width. So that's consistent with what we've learned in the course, that the directivity of 1 lambda dipole antenna, full wavelength dipole antenna, is larger than the directivity of half a wavelength dipole antenna, or equivalently, half power beam width of 1 lambda dipole antenna is smaller than half power beam width of half a wavelength dipole antenna. So theoretically speaking, half power beam width of half a wavelength should be about 78 degrees. We measured it to be about 80 degrees. And half power beam width of lambda dipole antenna should be close to 47 degrees. We measured it to be around 57.6. So our measurement for full wavelength dipole antenna was not as accurate as half a wavelength, but it still shows that its half power beam width is smaller than half a wavelength dipole antenna. The thing I want to discuss here is that when we did our measurement, we saw that the maximum signal for half a wavelength dipole antenna, so this was half a wavelength, this was full wavelength, was smaller than the maximum signal of 1 lambda dipole antenna by about 5 dB. So the question is why that's the case. If that's more directive, shouldn't we expect more signal? One thing that we need to be careful here is that when we are measuring, we need to also take into account the effect of impedance mismatch. As you remember from the course, if I have a full wavelength dipole antenna, what happens is that the current tends to be very small at the input port of the dipole antenna. When the current is very small at the input port of the antenna, the input impedance of the dipole antenna, which is voltage divided by current, would become very large because current, it becomes very small. Therefore, you're going to have a very large input impedance, and that creates impedance mismatch for you. And that's because of this impedance mismatch that we observe this gap between the maximum received signal. Okay, so we saw that we increased the length of the dipole from half a wavelength to 1 lambda. So we went from lambda divided by 2 to lambda, and now we're gonna increase it beyond lambda. So we know from the course that if you increase it beyond lambda, you're gonna start having out of phase currents on the dipole antenna. So that would be what we wanna study right now. So I'm gonna remove this arm and this arm, and this was an arm for 1 lambda dipole antenna. So I'm going to use now bigger arms to make it 3 lambda divided by 2. 1.5 lambda now would be the length of the dipole antenna. So now, as we change the length of the dipole antenna to 3 lambda divided by 2, now we have a new current distribution on the arms of the dipole. And because of the new current distribution, we're going to get a new radiation pattern that we're going to study. Again, as you know, this structure that we mounted the antenna and the transmitting antenna is for measurement of the E-plane cut. Okay, so now we want to collect the E-plane cut of 3 lambda divided by 2, 1.5 lambda dipole antenna. So we're in the E-plane cut, and at the display right now, we can highlight the half a wavelength dipole antenna so that you can see the half a wavelength dipole antenna. And then 1 lambda dipole antenna, that's highlighted next. That's our 1 lambda dipole antenna. But now we are start collecting 1.5 lambda. So as you see, we have a new lobe right now. So, and the pattern is, of course, because of the structure of the dipole is supposed to be symmetric. So we get a similar lobe. And now that is the lobe that we used to have for a smaller length dipole. But you see these new lobes appear. And the main reason for that is that as soon as you go beyond one wavelength, you start having out of phase current. And at this particular length, the effect of those out of phase current contribute to these new lobes that we have. So now so now I can save this as a new antenna, E-plane. So as you see, right now we have essentially a new radiation pattern. In this experiment, we want to check what's going to happen if we decrease the length of the dipole antenna. So this is right now half a wavelength dipole antenna. As you already know, this is not exactly half a wavelength, it's a slightly less than half a wavelength so that the reactance goes to 0. If it's exactly at half a wavelength, we're going to have some reactance. So to make reactance very small, we usually operate at a little bit smaller than half a wavelength, for example, 0.48 lambda or 0.45 lambda. So, but we want to go much smaller than that. We want to get to around lambda divided by 10 dipole antenna, or to be precise, 0.125. So to do that, I'm going to remove, let me have my wrist here. I'm going to remove these two arms. And what remains inside this dipole now has a total length of 0.125. So it's about lambda divided by 10 dipole. And now I'm going to collect 1/2 a wavelength E-plane cut. And I'm going to do it also for this new antenna, which is essentially a very tiny dipole inside this. Now I have removed the external arm of the dipole, and what we have right now is we have that internal dipole which has a length, total length of about 0.125 lambda, or about slightly bigger than lambda divided by 10. So what you have on the screen right now is the E-plane cut copole of half a wavelength dipole antenna. Now and as I mentioned, this is not exactly half a wavelength, it's slightly less than half a wavelength, so that we make the reactance very small. So now let's start the acquisition using this slightly bigger than lambda by 10 dipole antenna. Okay, so as you see, the signal is small because I made a mistake and I forgot to turn on the RF part. So I'm gonna stop the acquisition and we're gonna turn on the RF power. Now you're gonna hear this beep in the background. That means the RF power is on, and we're gonna do the experiment again. Okay, now we have our signal. So as you see, we are about maybe about 16 or 70 dB down from the other one. Now when the acquisition is complete, we can have a better guess. It's a little bit not symmetrical yet. The other side is bigger, so I mean we could look into that and see. Remember, the antenna is symmetric, but other things could be the problem. Okay, so this is what we got for the lambda divided by 10 dipole. I can store it under document 2 E-plane. So what we want to take a look is essentially the main thing that we want to take a look is our maximum signal level. So if I look at this side, uh, probably I'm about 16 dB down on this side of the screen. If I look at this side of the screen, the difference is more on the order of maybe 12 dB. So now the question is why that's the case. The question is why the signal that we are receiving for this small dipole, lambda by 10 dipole, is significantly smaller than half a wavelength dipole. And the main reason for that is the impedance mismatch that we have. If you remember, uh, for for a small dipole antenna, we have a very strong reactance in the form of capacitance. So that contributes to the smaller received signal that we have in this case. In the experiment that we performed with the lab volt antenna training system, we use this Yagi-Uda antenna at about 1 gigahertz to create, local plane wave at the antenna under test, because this is supposed to be tested in the far field. So we need to have, if you think of this as electric field, you need to have electric field that's relatively uniform in amplitude and phase, and also polarization over the area of this dipole antenna. So if you want to have a more accurate measurements, you need to use more accurate systems, and one of them would be compact antenna test range. So in compact antenna test range, the basic is similar in the sense that you have an antenna that creates for you plane wave, and then the antenna under test would be measured in that environment. So before going to the compact antenna test range for demonstration, let me tell you a little bit about the basic of how it operates. So our compact antenna test range essentially consists of three main components. We have a reflector, and we also have the feed of the reflector that illuminate the reflector. Now, if I want to compare it with the training system that we have, the combination of the feed and the reflector together would serve the same purpose as the Yagi-Uda antenna in the training system. So essentially, this is going to be creating plane wave for us. So the way that it works is that this feed is illuminating the reflector. So we are illuminating the reflector, and then due to reflector geometry, reflector is going to reflect back, and it's going to create plane wave at the antenna under test. Now, for example, assume that this is your plane wave that's going toward the antenna under test. Now, you would have plane wave over a certain geometrical domain that we call that quiet zone, and that would be essentially the area that at which we can perform measurements. Now, and then this would be your antenna under test, and this is going to rotate. When we were performing different types of measurement using the lab volt training system to perform cross-polarized measurement or to change the polarization of the transmit antenna, we would simply manually rotate the Yagi-Uda antenna 90 degrees to change the polarization. Now, with this system, if you want to change the polarization, you're going to use the computer of the system, and using the computer, you command the feed to rotate 90 degrees. So here you perform your rotation of the feed, and as soon as you do that, then this plane wave that, for example, before it was vertical, would be horizontal. So that's the way that you do that, and then you can perform your measurement. So this system is called compact antenna test range, or in abbreviation CATR. The range is usually referred to antenna measurement system. So we say this is a near field antenna range, we call it compact antenna test range, and so on. So, so if you look at this system is essentially creating plane wave for you to perform your far field measurements. And this is enclosed in an anechoic chamber. So you have an anechoic chamber with absorbers around on the walls and ceiling. So we're going to go and see how we can perform one measurement in the CATR. Okay, we are in the compact antenna test range. So what you see right now is the reflector of the antenna measurement system. So if you look at it, it's a reflector. And at the edge, we have a configuration that we call it a serrated reflector antenna. So essentially, at the edge, if we don't have those serration, we're going to have lots of diffraction. So essentially, this is to alleviate the edge diffraction. So this is our reflector antenna, and if we come closer and closer and closer, we would be able to see the feed of the system that illuminating this reflector antenna. So now we have our serrated reflector, and if I change the angle here, so you would be able to see this feed that is illuminating this reflector antenna. So essentially, when this feed illuminates the reflector antenna, by the way, the feed is covered by absorber. So we have absorber around the feed, and then this feed is going to be illuminating the reflector. And when the reflector is illuminated, the reflector reflects electromagnetic waves toward the antenna under test, and that would be the antenna under test. An antenna under test, or AUT, is mounted in the area that's quiet zone of the system. So that means over this area, we can assume that we have plane wave. So now this AUT tower can rotate in some different directions, and you can essentially get the cut that you want. So if I wanna make a one-to-one correspondence with the training system that we saw, this tower is essentially the tower for the antenna under test, and the combination of the feed of the reflector that we had here and the reflector itself would be essentially the role of the Yagi-Uda antenna that creates plane wave for us. So that's essentially our compact antenna test range, and we can take a look of a few data collection. As noted earlier, this is the feed of the reflector. So you see that this is a structure that covered with absorber. And if you want to change the polarization of the system, you need to rotate this feed. So now we're gonna just show you how the feed is rotated. So I'm asking Ehsan to rotate it, and so now it's actually rotating. It's hard to see, but now it has been rotated. So essentially, we change the polarization of the plane wave. Just before going to the compact range and performing copole E-plane, crosspole E-plane, copole H-plane, crosspole H-plane, just wanted to go over a couple of things with you before going to the compact antenna test range. So in the compact antenna test range, we're going to be measuring a horn antenna. So it's not exactly this horn antenna, but I'm just using this for demonstration. So if you look at this horn antenna, the E-plane of this horn antenna would be this plane. So if I have a plane like that, this would be the direction of maximum radiation, and this would be the direction of the electric field, and that would be your E-plane of the horn antenna. So if you want to perform E-plane measurements, So of course you need to move in the E-plane, so maybe you want to move like that, but remember that we usually, to do E-plane data collection, we rotate the whole thing. So that essentially be the rotation of our E-plane. So that's our E-plane. And sometimes it might be hard to identify E-plane, but if you look at the feed point of the horn antenna, which is here, which is vertical, you can guess that that would be the direction of the electric field and the direction of maximum radiation. You know it from the course, so this would be essentially your E-plane. So that's my E-plane. Now, H-plane is, of course, perpendicular to the E-plane. So if that was my E-plane, this is my H-plane. Now, if I want to do H-plane measurement, I'm going to rotate it in the H plane like this, right? So that's my E-plane. To do E-plane measurements, instead of moving like that in the E-plane, we rotate the whole thing like this and perform our E-plane. Now, if I want to do, let's go to a little bit more details. Now, let's assume I want to do H-plane. What we're going to see in the compact range is that I'm going to be first starting movement in the H-plane, so the antenna will move like that. So that's my H-plane. So the antenna is going to move like that. And instead of going all the way 360 in the compact range, I'll go from minus 90 to 90. So assume that this is minus 90. So it will start from here, minus 45, and then 0, and then come back again to plus 90. So that's our H-plane movement. We don't go to 360 for this demonstration. And then the very first measurement, we're going to illuminate our horn antenna when it's moving like that by this polarization. So this polarization is essentially not the polarization of the horn, because horn is expecting electric field to be in this direction. So now when I illuminate it with this electric field in this direction, and I'm moving it like that, I'm in H plane, but because polarization is not matched, it's going to be cross pole H plane, right? So that would be our very first measurement. Then what we're going to do in the compact range, we're going to rotate the feed of the reflector 90 degree. So when we rotate the feed of the reflector by 90 degree, essentially the illuminating electric field will rotate by 90 degree. Now, this would be the one that's illuminating our horn antenna, and I'm going to do exactly the same rotation. So I'm still in the H plane. So this time I'm going to collecting copole H plane. Now, the next step would be I want to go to E plane. So if I want to go to E plane, if you remember again, this is now our H plane. So if I want to go to E plane, this is my E plane. So to perform E plane measurement, I need to rotate the whole thing, right? So let's go back again. This was our last measurement. We did H plane, copole. So what we do, we're going to rotate this one 90 degree. And now we're going to perform measurement like this. Let me change my hand. So we're going to rotate it like this to perform E-plane measurement. But the polarization of the compact range is still like that. We haven't changed that. So if I perform measurements in this situation, although this is E-plane, but now remember now the polarization that the horn expect would be in this direction. But then the electric field coming to the horn is vertical, whereas this one is expecting horizontal polarization. So if I do this measurement, although it is E-plane, but it's cross-pole E-plane. Now, to do our final measurements, I'm going to rotate the feed of the reflector by 90 degree. So then the electric field is going to rotate. Now, I'm still in the E-plane, but now the polarization of the illuminating field is matched with the polarization of the horn. So essentially, I'm collecting copole E-plane. And similarly, when my measurement is done, I'm going to compare copole E-plane with copole H-plane to see if their peaks match each other. Okay, we are in the compact range right now. And as you see, this is the feed. The reason I'm taking another shot of the feed is that you're going to be hearing me saying that the feed is going to rotate 90 degree. So just wanted to show you the feed. And when the feed rotates 90 degree, essentially the polarization of the field that's coming out of the reflector is going to change. And during filming, I'm going to be focusing on the antenna under test, which is a horn antenna mounted on the tower. Right now, it is mounted at 0°. And in the measurements, we're going to be performing angles, measurement at different angles. And the starting angle is -90. So, and to +90. So we're going to be starting the measurement, and you can take a look at what's going to be the measurement. We're going to be collecting 4 cross poles. So now the antenna under test is going to the initial location, which is -90°. So now it's going to the initial location, -90°. So now it's almost at -90°. So it's gonna start collecting the data. The first one is cross pole H-plane. The noise that you heard is the rotation of the feed to make it cross pole to the antenna under test. Now it is cross pole, and this rotation is going to be H-plane because the feed creates cross polarized with respect to the antenna under test. This cut is going to be cross pole H-plane, so it's rotating, and the final destination that we set is +90. So now it is almost at 0°, and it's going for +90 right now. So as you see, the absorbers in the back of the horn, we could have done a better job, but this is just for demonstration in this case. So this is right now at +90, so it's gonna stop. Now this was cross pole H-plane. The next step would be copole H-plane. Now this noise in the background is the rotation of the feed to make the polarization match again. Since we have not touched the antenna under test, we are still in H-plane, but now the polarization is matched, it's copole, so it's becoming copole H-plane. Now we go again performing measurement. Probably we are now close to 45°. We're approaching to 0°, and it's going to -90°. So below the this tower, we have our microwave transceiver, which is a vector network analyzer, to perform our measurements. Okay, now we are done with H-plane. Now the antenna under test should rotate. So you see the antenna under test is rotating 90°. So we go from H-plane to E-plane. Now we are, in terms of polarization, we are cross pole to E-plane. So when I'm performing the measurement, this is going to be cross pole E-plane. So if you have missed the part that the antenna rotated, it wasn't easy to see, you probably can look at the absorber behind the horn antenna and compare it with the previous measurement. So then you can realize that the horn antenna has rotated 90° in this new shot. So yeah, that's our cross pole. We go to now +90. Now it's gonna stop here, and now you're gonna hear a noise in the background, which is the rotation of the feed to make the polarization match with the E-plane. Okay, now the polarization is matched, and now we can we're gonna do our last cut, and this is copole E-plane. Once we are done with the measurement, it's always good to check the E-plane cut copole with H-plane cut copole to make sure that the peak of these two cuts are on top of each other. If they're not the case, we need to check multiple things. One thing that you can always play with is the placement of the absorber in the anechoic chamber. Okay, now our measurement is done.